I am Dr. Dibyendu Dev from University of Kollani. I will give a course on topology. So, what is topology? In Greek word, topology means surface. So, we can say that topology is the study of a surface. What we do in topology? We try to investigate in topology to find an equivalence to topological spaces. Topological spaces are special kind of mathematical structure. For example, let us consider 0, 1 open interval and say any other open interval. Whether these two topological space equivalent or not. If we can here, if we observe that we can stretch the 0, 1 open interval to another open interval. So, these two topological space are same, or let us consider the circle. So, we can by radial projection we can push the circle to a square. So, these two are topologically equivalent. In fact, topology can be called a rubber sheet geometry or qualitative geometry. Or for example, let m and n be two letter in English alphabet. Then n can be stretched to n or n can be stretched to m. So, m and n are equivalent to a topologist. But if we consider m and the letter b, these two, it is not possible to convert m just by stretching or such way to b. So, these two will not be topologically equivalent. So, these are intuitively saying what we are told up to that, these are intuitive. So, we need some formal definition to mathematize this. So, let us come in the presentation. In order to get the notion of continuity in abstract case, one needs a notion of properly defined nearness, so that one can say about transformations of geometric object which preserve nearness. The idea is that if one geometric object can be continuously transformed to another, then they will be equivalent. For example, say let us consider circle. If we observe that closely, that circle can be continuously transformed to a square or a triangle. So, they are topologically equivalent. Or let us consider an open interval of size 1. Then this open interval can be continuously transformed to another open interval of size 2. So, these two open intervals are topologically equivalent. But if we consider an open interval and a circle, these two will not be topologically equivalent. Why? Because this is just intuitively saying that if we take a point from the open interval and if we take a point in the circle, the open interval lefts two component, but the circle lefts just only one component. So, the term used to describe two geometric objects that are topologically equivalent is homeomorphic. That means, from now if two geometric objects are equivalent, we will say that they are homeomorphic. In this terminology, a circle is homeomorphic to a square. This happens by the radial projection. An open interval of length 1 will be homeomorphic to a greater open interval or smaller open interval. Of course, m and n will be homeomorphic, but m and h will not be homeomorphic. This can be quite difficult in general, that whether two topological space are equivalent or not. So, to show that two topological space are not equivalent, it requires harder work. But to get the proper notion of topological spaces, first we have to get a proper notion of continuity. So, let us start from the elementary real analysis. We know that in the elementary real analysis epsilon delta definition of continuity. But this definition also comes in the elementary real analysis, that is, a function f from R to R is continuous if for each open set O in R the inverse image f inverse O is also an open set. We will use this definition to define continuous function between two topological spaces. This definition in fact preserves continuity. So, in trying to find a satisfactory definition of continuous function or topological space, we would like to consider a finite set, discrete set of points as a space, or equally whole uncountable continuum of points such as real line. One of our nice geometrical surface should qualify under this definition, and also sets of functions such as the set of continuous complex valued functions defined on the unit circle on the complex plane. Let us consider an example, a very beautiful example of topological spaces, which is called Mobius strip. One beautiful example of geometric object is Mobius strip, which you have seen in the last slide. What we do to construct a Mobius strip, let us take a plain piece of rectangular paper, then identify the left side and right side, making the direction opposite. Then what happens? If one starts to run from a point, then when he returns back to that point again, his direction changed. So, this is orientation preserving. This Mobius strip will be act as a very important example in our whole study. Now, we will give a formal definition of topological space. By a topological space, we mean a non-empty set X and a subset of power set of X which satisfy the following properties. First one is both empty set and whole set X is in R in O. Second one is O is closed under arbitrary union. Third one is O is closed under finite intersection. Then O will be called a topology on X, and X and O simultaneously will be called a topological space. From now we will avoid O, and generally we called X as a topological space. Our most known example of topological space is set of real numbers. This is generally called usual topology. Here what we know from elementary real analysis, what as open set, here open set also are those, and we can easily verify that open sets here satisfy these properties. That means in R, empty set is open, whole R is open. We know in R, arbitrary union of open set is open, finite intersection of open sets is open. Let us give some other examples. Let X be a non-empty set and script O be the power set of X. Then it is easy to observe that XO is a topological space. It is called discrete topological space. In mathematical situation, discrete topological space is extremely important. Another example of topological space is indiscrete topological space. Here we take as open sets only empty set and X. This is not so much important topological space, but I have given just for example. Let us consider another example of topological space. Let X be the finite set A, B, C, and script O be considered. Script O contains empty set, whole set X, singleton set A, singleton set B, and the set containing A, B. We can verify that this is a topology on X, because this is closed under arbitrary union and closed under finite intersection. So, this is also a topological space. Let us consider some more important topological space. This is called cofinite topological space. So, how this topological space is defined? Let us consider an infinite set X, and let us consider tau Cf is the collection of all those subsets of X whose complement is finite. Then we can prove that tau Cf is a topology on X, and X with tau Cf is called cofinite topological space. The proof is very easy. You can see the proof. Empty set belongs to tau Cf by vacuously. X obviously belongs to tau Cf. Now let us consider A1 and A2 belongs to tau Cf. That means complement of A1 and A2 finite. Then X minus A1 intersection A2 is equal to X minus A1 union X minus A2. Now as A1, A2 both belongs to tau Cf, then X minus A1 is finite, X minus A2 is finite. So right hand side is finite. That means X minus A1 intersection A2 is finite. That means A1 intersection A2 belongs to tau Cf. So tau Cf is closed under finite intersection, and it is obvious that tau Cf is closed under arbitrary union. This is a generalization of the previous example. There we told about that cofinite topological space. Now I am telling about that co-countable topological space. For this, so let us take a set with cardinality at least uncountable. So let X be an uncountable set and consider all those subsets of X whose complement are countable. Then this collection will be a topology on X. Generally this is denoted as tau CO and called co-countable topological space. Proof is almost as the above, so we will not repeat the proof here. Another example, let X be a plane, that means R2, and let O consists of empty set and X, and all open disks with center at origin, then clearly O will be a topology on X. Next, we define an interesting topology. This consists some number theoretic flavor. Before that, we define the following notion. Let X be the set of all non-negative integers, that means 0, 1, 2. For a subset of X, let us consider the cardinality of A intersection 1 to n as this. Let us define tau is equal to all those subsets of X such that 0 does not belongs to A or 0 belongs to A and limit n tending to infinity, cardinality of A intersection 1 to n by n is equal to 1. It can be proved that then tau is a topology on X. Clearly empty set belongs to tau and obviously X belongs to tau, because X intersection 1 by n, its cardinality by n, this is equal to 1, so the limit will go to 1. Now let AB belongs to tau, that is limit of cardinality of A intersection 1 to n by n is equal to 1, and similarly limit of cardinality B intersection 1 to n by n is equal to 1. Then limit cardinality of A complement intersection 1 to n by n is equal to 0, and limit cardinality of B complement intersection 1 to n by n is equal to 0. This implies that limit cardinality of A complement union B complement intersection 1 to n by n is equal to 0. Since X minus A intersection B is equal to X minus A union X minus B, we have the desired result. As elementary real analysis, we declare here a set in a topological space to be closed if its complement is open. So In a topological space, a set will be called closed if its complement is open. Then following can be proved. Theorem. Let X be a topological space, then the following conditions hold. Number 1, empty set and X are closed sets. Number 2, arbitrary intersection of closed set is closed. Number 3, finite union of closed set is closed. Empty set and whole set X are closed because their complements are open set, and rest of 2 follows by elementary set theory result. We are just telling about the arbitrary intersection of closed set is closed. So, let us consider a arbitrary collection of closed sets. Let us consider it as F alpha such that alpha belongs to gamma, where gamma is an index set. Then by definition of closed sets, each x minus alpha is an open set. So, this is a collection x minus alpha such that alpha belongs to gamma is a collection of open sets. So, since open sets are closed under arbitrary union, so their union will be open. That means as their union is open, its complement is closed. That means arbitrary collection of closed set is closed. Again, as elementary real analysis, we can define limit points, interior points in arbitrary topological space also. So, let us start the definition. Let X be a topological space, A subset of X, X be an arbitrary point of the topological space. Then X will be called a limit point if any open set containing X intersect A in a point other than X. For example, in the usual topological space R, every real number is a limit point of the set of rational number, or every real number is a limit point of the set of irrational number. In an arbitrary topological space, a point which is not a limit point will be called an isolated point. Now, let us define what is called interior point. Definition: let A be a subset of a topological space X and X be a point in A. Then X will be called an interior point of A if there exists an open set containing X which is contained in A. We know from elementary real analysis that a set A is open if and only if each of its points is an interior point. That will hold here also. The set of all limit points of a set A will be called derived set. By the closure of A, we will mean A along with limit points, and it will be denoted by A bar. The set of all interior points of A will be denoted by A interior. So, what will be the closure of Q in the usual topology of R? Closure of Q will be whole R, and interior of Q will be empty set in the usual topology of R. Let us put a question. What will be the interior and closure of the following sets? First one is all xy such that 1 less than x square plus y square less or equal to 2. That means it is a annular region. The outside boundary includes then this annular region, but the inside boundary is not in the annular region. So, what will be the closure? In the closure, inside boundary will include, and to determine the interior, just we have to exclude the outside boundary. Now, another question: what will be the closure and interior when both axes have been removed from R2? When both axes have been removed from R2, its closure will be whole R2 and interior will be the same. These are the some following properties, some easy properties of closure. Let X be a topological space, A, B be two subsets of S. Then let us the following will hold. Number 1, if A subset of B, then A bar will be contained in B bar. Number 2, A union B bar will be equal to A bar union B bar. Number 3, A intersection B interior will be equal to A interior intersection B interior. The proofs are easy, still we are telling this. One is obvious. For part 2, let us consider X belongs to A union B closure and let U be an open set containing X. Then by definition, obviously U intersection A union B is non-empty. This means that either U intersection A is non-empty or U intersection B is non-empty. This implies that either X is a limit point of A or X is a limit point of B. That means X belongs to A bar union B bar. So A bar union B bar is contained in A bar union B bar. Conversely, let X belongs to closure of A union closure of B and U be an open set containing X. Then either U meets A or U meets B. That is, U must meet union of AB. So X is a limit point of AB. So this gives the reverse inequality. The following are some properties of closure and interior. Let X be a topological space and A be a subset of X, then the following hold. A interior is the largest open set contained in A. A closure is the smallest closed set containing A. A is an open set if and only if A is equal to A interior. A is a closed set if and only if A is equal to closure of A. So let us start the proof. Number 1. If X belongs to A interior, then there exists an open set B such that X belongs to B subset of A. We have that B is subset of A interior. In fact, for each Y belongs to B, B is an open set contained in A and containing Y. Now let O be an open set contained in A. Then for each X belongs to O, there exists some open set B such that X belongs to B is contained in A. This follows from the definition. That is, each element of O is an interior point of A, so that O is a subset of A interior. The proof of the second. Let X is in the complement of A closure. That means X is not a limit point of A. Then there exists some open set O containing X which misses A closure. We claim that O also misses A. If not so, then there exists some Y belongs to A bar minus A such that Y belongs to O. This implies that O meets A, which is a contradiction. Therefore, A bar is closed. To prove that A bar is the smallest closed set containing A, let K be a closed set containing A. If possible, let there exist some Y belongs to closure of A minus K. Then there exists an open set O containing Y which misses A, which contradicts that fact that Y belongs to A bar. This completes the proof of this theorem. This is an important, very important example. This is called topology sine curve. The graph is shown in the picture is called generally topology sine curve. Its description is that this is the all points x sine 1 by x such that x greater than 0. Now, if this graph is removed from R2, what will be the interior and closure? We can observe that if this graph is removed from R2, then its interior will be just this set, but its closure will include the set singleton 0 cross minus 1 to 1. Now we will discuss convergency. Like elementary real analysis, we can also define convergency here. We will define in this fashion: a sequence xn will be called converging to some point x if for any open set containing x there exists some n0 belongs to n such that xn belongs to n for all n greater or equal to n0. We have seen in the elementary real analysis that a sequence converges to only one limit point, if at all it converges. Whether it also holds in arbitrary topological space or not, we will examine. But before that, we will define two notions of topological space or two properties of topological space. Definition: let X be a topological space, then X will be called T1 space if every finite set in X is closed. Number 2, X will be called Hausdorff or T2 if any two distinct points can be strongly separated by disjoint open sets. This is very easy to show that every Hausdorff space is T1. This is done in the slide. Now, if we observe that in cofinite space any sequence converge to any limit point. Why this happens? This happens because cofinite set is not a Hausdorff space, but in a Hausdorff space a sequence can converge to at most one limit. So, we can get this following proposition: in a Hausdorff space each sequence can have at most one limit. Proof: let X belongs to X and Y not equal to X. Then there exist disjoint open sets U and V containing X and Y respectively. So, we have seen that in the cofinite space a sequence converges to all points of the set, but this does not happen in Hausdorff space, since in a Hausdorff space two different points can be strongly separated by disjoint open set. So, a sequence can converge to at most one point, which you can see from the proof of the theorem. So, in this module we have basically defined topological spaces and given some examples of topological spaces. With this we finish the module.